Welcome to a new episode of Frame Minds Engineering. Today we're going to discuss the topic of beam structural design. We're going to start by discussing the different failure modes of beams. A beam can fail in so many different ways. Some ways are instantaneous, like ductile yielding, brittle failure, excessive deflection, or even buckling. These failures can happen either through a bending moment or shear or a combination of both. There are also other modes of failure that happen over a long period of time, such as fatigue, where cyclic loading is applied until a crack in the beam is formed. There is also stress corrosion cracking, or even creep, where the same load is applied for an extended period of time and plastic irreversible deformation occurs in the beam. We're also going to discuss how different cross-sectional shapes are susceptible to different strength limit states. We're also going to discuss how to find the governing strength. So let's talk about the failure modes for the beams. The first failure mode is flexural yielding. When a moment is applied onto the beam, and the beam fails due to flexural yielding, the stress distribution would look as follows. We can see in this case that the top flange or the compression flange has reached the yield stress limit. Yielding can either occur in the top flange or the bottom flange. In CFY and TFY refer to compression flange yielding and tensile flange yielding. However, if the beam is still elastic, the stress distribution would look as follows. Flange local buckling. When a beam experiences bending stress, one of the flanges would be loaded in compression. This will lead to a buckling in the flange as seen below. Here is a real-life example on how this would look like. When a beam is loaded vertically or is experiencing bending moments, provided that the web is not thick enough, the following will occur. This phenomena is called web local buckling. This is lateral-torsional buckling. This happens when the beam is excessively long without being supported from the sides. Let's have a closer look how this happens. When a beam is vertically loaded, the load will not exactly coincide with the beam's center of mass. Because of this load eccentricity, the beam will start to twist. As the beam twists, this eccentricity becomes more and more severe. This would continue until finally the beam would buckle about its minor axis, because as the beam twists, more and more of the bending moment is being resisted by its minor axis instead of its major axis. Because there is no clear distinction between flanges and webs of round hollow sections, the following mode of failure is called local buckling. But in fact, this happens for the exact same reasons as flange local buckling. When the hollow section is experiencing a bending moment, one of its sides will be under compression. This will result in the failure mode we see in the middle, which is also represented in a finite element software. To further understand what happens, let's zoom into this region. First, the pipe is straight, but then as the moment is applied, the compression side buckles. This is most likely to happen when the wall thickness of the hollow section is really small compared to its diameter. Leg local buckling is a very similar phenomenon that happens in single angles, where the compression side buckles because the thickness of the leg is small relative to its width. The highest possible nominal flexural strength is the plastic yielding limit. This means that if the beam fails due to any other reason other than yielding, the full potential of the section is not utilized. In order to make sure that the section fails due to yielding, we have to make sure that we end up on this position in this diagram. This diagram shows the flexural strength of the beam relative to the slenderness ratio of its flange. The leftmost region is called the compact region. In this region, the flange is thick enough such that flange local buckling would not occur, unlike in the slender flange region, where the flanges are really thin and are very susceptible to local buckling. A slender flange looks like this, while a compact flange looks like this. The limiting slenderness ratios can be extracted from this table shown on the right, from the AISC Specifications 360, and this specific row is used to determine the slenderness ratio of the flanges of an I-beam, the slenderness ratio of the web of the I-beam, or any other shape for that matter, can be found in the AISC Specifications 360. So what is the effect of large unbraced lengths on the flexural strengths of the beam? Let's start by defining the unbraced length. The unbraced length is the distance between points in which the beam is not allowed to twist. Here we can see that this beam is bolted on one side, and on the other side, the beam is laterally supported by another beam, and thus this is the unbraced length of this beam. Similarly to the previous diagram, the larger the unbraced length of the beam is, the weaker the flexural strength. Mainly, this is due to elastic lateral-torsional buckling, but it can also be that the lateral-torsional buckling is inelastic. When the unbraced length of the beam is of length LR or higher, then the flexural strength of the beam is less than 70% of that of the flexural yield limit. Another contributing factor is the factor C sub B, which is an indicator of the moment distribution in the unbraced length. On the bottom right are some examples of C sub B values for simply supported beams. The following is a table that summarizes the possible limit states for each shape. This table makes beam design easier, as the structural designer does not need to go through all the equations of different failure modes, but rather only the ones listed in the table for the specific shape to be used. Let's start with the I-beam or a W-beam that is loaded about its major axis and symmetrical about its axis. This section has compact flanges and compact webs. The only two possible modes of failure to be checked are yielding and lateral-torsional buckling. This means that in order to assure that this beam fails due to yielding, the unbraced length should be kept short enough such that the beam will not fail due to lateral-torsional buckling. We can see in the next shape that if the flange is slender, then the two possible modes of failure are lateral-torsional buckling and flange local buckling. Notice that the section can't possibly fail due to yielding because the flanges are not thick enough. The following is for doubly symmetrical I-beams that has the following combination of slenderness for the flange and the following combination for slenderness for the web, or a single symmetrical beam, both that are loaded about their major bending axis. Such beams, again, cannot fail due to yielding and will fail in one of these four limit states. One is the compression flange yielding, the other lateral torsional buckling, the third is flange local buckling, and the fourth is the tensile flange yielding. Next are the same sections, but with slender webs. These sections will fail due to the same four conditions as the previous beams. Next are I-beams and C-channels bent about their minor bending axis. Although these sections are most likely to fail due to yielding, the yielding flexural strength of these members is so much less than those of beams bent about their major axis that this is extremely inefficient. Next are rectangular hollow sections. These sections can fail due to yielding, flange local buckling, web local buckling, or lateral torsional buckling, depending on the case. Next are circular hollow sections that can fail due to yielding or local buckling. Double angles or T sections can fail due to yielding, lateral torsional buckling, flange local buckling, or web local buckling, depending on their dimensions. Single angles can fail due to yielding, lateral torsional buckling, or leg local buckling. Circular rods or rectangular sections can only fail due to yielding or lateral torsional buckling. Unsymmetrical shapes need to be checked for all limit states. Now that we are done with bending, let's discuss the topic of shear. So what are the failure modes of I and C sections under shear? The first one is web Yielding. The shear stresses in these sections are mainly resisted by the webs. A sub W is the area of the web. In this case, it is H multiplied by the thickness of the web. F sub Y is the yield strength of the material. C sub V is called the buckling coefficient of the webs and is a measure of the ratio of the height of the web to the thickness of the web. The second mode is web buckling. Web buckling uses the same equation as web yielding while adjusting factor of C sub V. If the ratio of the height of the web to the thickness of the web is less than a certain limit, then C sub V will be less than 1 and thus reducing the shear strength of the member. What about the shear behavior in angles and T's? In angles and T's, the webs are also the main shear resisting elements. In order to understand why the webs are the main resisting elements, we have to look at the shear stress distribution across the cross-section. So let's have a look at the side view. So here's how the shear stress distribution looks like. We can see that the contribution of the flange is really minimal compared to that of the web. Because we assume that the stress is uniformly distributed across the web, this idealization removes the peak values that happen in the middle of the web, and thus to compensate for that, the factor 0.6 is added into the strength calculation factor. And we can also observe that the shear strength is again dependent upon the factor B over T, which is the ratio of the width of the web compared to its thickness. The same can be said about rectangular hollow sections. In rectangular hollow sections, however, the web area is 2 times the height of the web times the thickness of the web, because there are, of course, 2 webs. When it comes to round hollow sections, the shear behavior is slightly different. Because the round hollow sections have no distinct web and flanges, the contributing shear area is considered as half of the cross-sectional area. Looking at the following equations and the 3 limit states, and considering that D is the outer diameter of the pipe, T is the wall thickness of the pipe, and A sub G is the gross cross-sectional area of the pipe, whenever the ratio of the diameter of the pipe to its thickness is greater than or equal to 100, most likely one of the following 2 cases will govern. But if that is not the case, then the yielding case will govern, with L sub V being the distance from the point of the highest shear to the point of zero shear. Last but not least, let's discuss the serviceability limit state. When it comes to ground floor levels or intermediate floor levels, the maximum allowed deflection is usually the length of the span divided by 360. And when it comes to a roof level, the maximum allowed deflection is the length of the span divided by 240. Please notice that the dimension L is in feet and the overall deflection is in inches. Don't forget to like and subscribe and turn on the notification bell. Thank you for watching.